Let's take a look at the basic exponential relations equation, and we're going to then start relating that to a table of values and to a graph. So we have on the right here just kind of a basic graph showing exponential growth, so the blue one going up towards the right, so increasing, and then showing exponential decay, so going down towards the right in red. And let's keep that in mind as we are looking at our basic equation. So our basic equation, I'm going to zoom in a little here, is y is equal to a times b to the power of x. Now, that exponent of x is only on the letter b, or whatever number ends up representing the letter b. So it is not on the letter a. So when we are using our equation, we need to make sure we take that into account as we are doing our calculations. So let's get into what the different parts of the equation are. So the a, try that again. So the a, this is an initial number. So usually we are looking at the growth of a population or the amount of something. So this is like the starting number, the number that you start out with. Now b, this is the growth or decay factor. And let's just get a little deeper into what B actually is. So if we are looking at growth, B is equal to 1 plus R. And I'm going to say what R is in a moment. And if we're looking at decay, B is equal to 1 minus R. And the R is the growth or decay rate. And what this is that sometimes we're given a percent. So something is growing at a rate of 10%. And we take this percent and then we put it into a decimal. So it's the growth or decay rate written as a decimal. Okay, so you're taking a percent and then you're turning it into a decimal. And remember that we do this by dividing by 100. Now, we haven't gotten to x yet. So x, this is our time period. Because usually we are looking at the growth or decay of a population over time. So now that we have that, we are going to get into looking at a table of values and then graphing that table of values. So I'm just gonna change the zoom on here for a moment. So our table of values here, we're given days and then we're given a population of something. Doesn't quite matter what it is at this point. So at day 0, this is our starting time. We have a population of 40. And then after 1 day, we then have a population of 60. After 2 days, a population of 90. After 3 days, a population of 135. So we are going to be taking that information and we are going to be graphing it. And then we're going to take that information and we are going to write an equation with it. So let's start off with graphing. So we have a grid here on the right. So I'm going to be shifting back and forth just a little bit. Maybe I can zoom it right there. And first off, we need to notice that the highest number we need to represent on our graph is 135. And on this graph, if we count all of the vertical little squares or spaces, there are 20 spaces. So what we want to do is we want to figure out how much should we be counting up by, because we need to count up by the same number each time. So I am going to take the number 20, so 20 squares, and then I'm going to divide it by 135. Now that's going to give me 6.75. So this is the smallest, this is the smallest number that I can count up by in order to fit 135 on our grid. Now, it doesn't really make sense to count up by 6.75 though. That would be very difficult. But what we can do in this case is we can count up by 10. So if we count up by 10 and there are 20 spaces, then we should reach 200 by the time we get to the top. Now I'm going to start marking out our scale, because on the vertical, we already have a scale on the horizontal at the bottom. And I'm not going to mark out every single square because that would then be way too many and it would be very squishy. So each square though is going to stand for 10. So I'm actually going to just mark out every 20. And it's nice when the number actually goes higher than what we're given on our table of values, so we can kind of see where things are going once we've graphed our curve. Now we need to label our axes. So along our vertical axes, this is our population, right? So our number of whatever, a species or something. Now along the bottom, we are told that we have time in days. So we need to write the word time and then put days in brackets right there. You could also just put days, but the day part is the most important. Now we are going to graph our information. So at day 0, we have 40 in our population. At day 1, we have 60. At day 2, we have 90. And at day 3, we have 135. Okay, so as you can see, this isn't a straight line going up. This is a curve that is slowly increasing. So now we're going to do a curve and we're going to put an arrow on the end to show that it just keeps going. So here we have done our graph, and ideally if we had more information we would also write a title for our graph. So I'm just going to write the title as population increase. If we knew what it was, ants, mice, or something, we could add in that detail as well. Okay, so now we've graphed it, and now we're going to write an equation that represents this. And what we need to do is we need to go back to our table of values, and we are going to calculate something called the common ratio. So the common ratio compares the numbers in the y column, right? We have like the x column, the y column. So it compares these numbers to each other. And what we want to do is we want to take the bottom number, and we're going to go in pairs here, and then divide it by the top number. So 60 divided by 40, that's going to give us 1.5. So I haven't rounded that or anything. The next one, 90 divided by 60, that is going to give us 1.5. And lastly, 135 divided by 90 gives us 1.5. So this is our common ratio. So from one number to the next, they all have the ratio of 1.5. So this is bottom number divided by top number. And this number actually ends up being our B value. So remember our B value, which is the growth or decay factor. So this is our B. And in this case, it is a growth factor. So this is our growth factor because B is greater than 1. So if you haven't, please do go back and take a look at the notes for this unit because it goes into a little bit more detail about that. So we have our B, which is our growth factor, and now we need to have our A, which is our initial number. So right here, we start off with 40. So this is our initial number right there. So let's write down what we know so far. So A is 40, B is 1.5, and then x. We don't know what x is, and we don't need to know it in order to write the equation, because we're just writing a representation of all scenarios. If we wanted to, we could put in a number for x and then figure out what the population would be after a certain amount of time. So we are working with y is equal to a times b to the power of x. Now we're going to put in what we know. So a is 40, and then b is 1.5. So we have 40 times 1.5 to the power of x. And remember, that 1.5 is to the power of x, the 40 is not to the power of x.